In this series of lessons, we're trying to get to the bottom of how are fractional numbers represented in binary systems. And we know that floating point values are what we typically use when representing numbers with fractional components in our program. So we're working towards how do we understand floating point representations in binary, and what does that even mean? Well, in the previous lesson, we looked at fractional representations in both base 10 and in base 2. If you're not familiar with how to represent fractional values in base 2, using binary points and thinking about powers of 2 that are like 1/2, 1/4, 1/8, so on and so forth, I would encourage going back and watching that lesson first. Otherwise, let's take an intermediary step. Before we get to binary floating point, let's think about what the world might look like if we were thinking in terms of decimal floating point. And then we'll be able to translate that knowledge to binary floating point. Before we get into what do we mean by floating point, let's think about an example that you should have some familiarity with, which is scientific notation. And the question here is, what are the actual decimal numbers represented in base 10 with these scientific notation expressions? And the first one is pretty straightforward, right? This is just an algebraic expression. We have 1.10 and we're multiplying by 10 to the power of 2. And we know that in scientific notation, we're always doing something that's a power of 10. This is going to increase the magnitude or decrease the magnitude by some power of 10. And we're otherwise trying to encode only our significant digits in the first part of our number. And by a convention, we're always going to assume that only the ones position is going to be represented on the significant digits of our scientific notation. And then we'll change the magnitude of that using the multiplier here, or the scaling factor, right? And so what we can do is we can work this out. So this is 1.10 multiplied by 100, and we know that that's going to be 110, right? There's a trick we learn in our earlier years where this 2 is telling us, well, we know that we're raising 10 to a power of 2, and because each of our positional values in our numbers is a power of 2, this tells us what we can do with our decimal point. So the sort of trick that most teachers try and teach us in our earlier years is if we're increasing by 10 raised to the power of 2, we just move our decimal point 2 positions back, and boom, like we could have easily computed this as 110 using that little trick. And that trick is going to wind up being applicable when we think about binary representations of effectively scientific notation or floating point notation in binary. Same idea with 2.11 e to the -1, but we should first translate this into what we know this means, but we just use this convention because it's what our calculators tend to use. So 2.11 multiplied by 10 to the -1, right? And so we're okay and we're comfortable with this idea that e being like 10 exponent -1 is like something we can depend upon. We just know that means 10 raised to the whatever comes after it. And that's going to be an important thing to remember that we're comfortable with as we move towards thinking in terms of base 10 floating point numbers as well. We can just assume there's a built-in 10 raised to some power here, and that power is all that really matters to be specified. But we need to know that like some digits are for our significant digits and some digits are for our exponents digits. And so we're breaking those two down here. And so 10 to the -1 is 1 over 10 or 0.1. And we know using that trick, when we multiply some number by 1 over 10, we're effectively moving a decimal place back by 1. So this would be 0.211, right? We're effectively putting 2.11 over 10, and this has the result of decreasing its magnitude by 10, or by 1 power of 10. So hopefully this feels familiar, and scientific notation is something that we've been taught, and it's going to wind up playing a significant role in how we think about what floating point actually is in computation. So now let's talk about the constraints here that we're up against and the fundamental problem that we have when thinking about floating point representations. And that is, with digital systems, we've kind of come to be comfortable with this idea that our binary encodings are going to have some fixed size to them in order for our systems to be efficient, and in order for us to think of them as primitive values that we can work with and depend upon the performance and the storage requirements of. And so the key design question here that we need to face, which is a really fun question to think about and has some really interesting trade-offs. And the reason why it's a design problem is because there's not a right way of doing this. And ultimately, we just need to pick a way that has the best set of trade-offs for whatever problems we're trying to solve. And so if we imagine we have a fixed number of digits that we're able to use to encode a number in scientific notation or in floating point, then how do we use those digits? How do we allocate those digits to the significant digits versus the exponent? And what are the trade-offs of going in one direction or the other? So I want to pose this problem to you as an actual design challenge. I want you to try thinking of how would you represent a fractional value with a finite number of base 10 digits? And the formula that's going to drive this design discussion is, imagine we're trying to represent some number x. And the way that we're going to represent it is we're going to have an implicit inherent 10 raised to some power e. And that e is going to be something that needs to be specified as part of our number, as part of your digit budget. And then we're going to multiply that by c, which is going to be our significand or our significant digits. And you're going to think of this as your coefficient, or sometimes you'll hear this in a very technical sense, the mantissa. We're going to, just like in scientific notation, assume that there's an implicit decimal point after the very first digit of c. Okay, so what do I mean by this? Well, let's imagine that we've got c that's going to be, let's say, 3 digits, 1, 1, 0. If our c was allocated 3 digits and we represented those digits and we chose 1, 1, 0 as them, we're saying there's an implicit dot here, right? That decimal point is just implicit at this point. And we can do that because this is the same in scientific notation, right? With scientific notation, you assume there's only one value in the ones position, okay? So with that set of knowledge, I'm gonna say that you've got 3 positions, you've got a budget of 3 digits places to work with. So how you use those 3 digits and how you allocate them to either E digits or C digits is going to be up to you. And so let me be a little bit more explicit here. And let's say that we, as one example, maybe we say that, okay, this is my E digit, and these are going to be my C digits or my significand. Then what we would say is, okay, let's say this is 2 and this is 9, 9. What we would do or think of in terms of translating this into the expression above is we're saying, okay, this is going to be, x is going to be 10 to the second multiplied by 9.9, right? And that's the number that this would encode in base 10. But how you would choose to allocate E and C is entirely up to you. If you gave 0 digits to E, you should assume that E is 0. And if you gave 0 digits to C, you can assume that C is 1, because multiplying 10 by something else would give you, multiplying 10 to the power of E with anything other than 1 would give you, like, if you assumed it was 0, you would have 0 for every possible representation. But I'm going to tell you that I think you're going to find a happy medium somewhere in the vicinity of giving 1 or 2 digits to either E or C. And I want you to think about what the trade-offs of doing making those allocations are. Right? So you have 3 positions to store base 10 digits, 0 through 9, and represent numbers in this way. And for whatever system you choose, and I would encourage you to try thinking through a system different than the one we just did. How many positions would you allocate to E? How many positions would you allocate to C? What is the largest number you can represent? What is the smallest non-zero number you can represent? And what are the fundamental trade-offs between allocating digits to E or C? And there is a trade-off here that is important to think about and does have real ramifications in how we represent floating point values. The next question is this one's a little bit less important and fundamental than the first one, but how would you, if we needed to be able to represent negative exponents, how would you do that without having a negative symbol? With negative e's, you could represent fractional values that would allow us to specify numbers that were fractional, less than 1 but greater than 0. Right, so we're not talking about making a negative number here. We're talking about making a negative exponent. And so can you think of a way that with only 3 positions, you could somehow modify this formula to somehow allow some negative powers of 10 for that, that magnitude or order of magnitude or exponent with still using this mechanism? And there's going to be a trade-off there as well. So think about these questions and give yourself a chance to think through them. Pause the video here, and then we'll come back and discuss some of the trade-offs in thinking about the design of how we choose to use each of these digits. All right, so let's talk through a possible design here. What if we chose 0 exponent digits and gave all 3 of our digit budget to our significand or our significant digits? What that would mean is the smallest non-zero value that we could represent is 0, 0, 1. And because we're assuming that when we use 10 or 0 exponent digits, that the order of magnitude is 10 to the 0 or 1, we're just going to multiply whatever number we come out with here with 1. And we mentioned that there's an implicit decimal point at this position after the very first digit. So this would be the same as 0.01, right? And the largest value that we could represent is 999, which would be 9.99. And that's already represented in base 10. There's no additional computation we need to do to raise by some magnitude, right? So in this design, we're able to represent the values between 0.01 and 9.99. And we'll talk about precision and how precise we can be in the next slide. So how do we think about precision? And this is an important factor to consider when thinking about floating point numbers. Precision is, we can think about as what is the next closest value we can represent in some encoding. And from the smallest non-zero value, we're asking what is the next smallest non-zero value and how far apart are these two values? So if we looked at the smallest non-zero value and subtracted the next smallest, so again, if we imagine the implicit decimal point here in these positions where we have 0.01, 0.02, these are the 2 smallest non-zero values that can be represented. And if we take the difference of those, that tells us the precision that we have available in this range of our numbering system. And we have 0.01 on the precision. So that means that each next number we can represent within this range is 1/100th away from the next number closest to it. And at the top of our scale, we see that the same thing is true, right? 9.99 is the largest number, 9.98 is the next largest number, and we can represent, again, with 1/100th of a precision value between each of these numbers. So when we don't have any exponents allocated in our budget here, notice that we have a constant level of precision throughout our entire number, or our entire domain of possible numbers we can represent with 3 digits in this system, right? How many digits can you, or how many different combinations can you form overall with 3 digits available to you in base 10? There are 1,000 different combinations, right? We have 10 digits per position. So 10 times 10 times 10 is 1,000. So there are 1,000 possible different numbers we can represent. And notice that we can represent 1,000 different numbers between 0 and 9.99. We can't represent 10, but we can represent 1,000 different values between 0 and 9.99. So let's think about a different design proposal, which was the one that we looked at and gave a quick example of on the first slide that was proposing this design problem. The smallest non-zero value we can represent in a design proposal where we allocate 1 digit of our budget to the exponent and 2 to our significand or our significant digits means that the smallest non-zero value is once again 0, 0, 1, but this actually has a different interpretation and different meaning because of how we're treating these digits than 0, 0, 1 did in the previous system, right? So here what we're saying is take that 0 in the first digit, and that's going to be our exponent digit, right? That's going to be what we raise our order of magnitude by. And in these next positions, we're saying, okay, this is, once again, we're going to assume an implicit decimal point here. So 0.1, right? So what we're saying is this sequence of digits in the system encodes this formula, right? And when we compute this out, we get 0.1, right? So notice this is not as small as of a number as we could represent before. Before we could represent 1/100th. Here we can only represent 1/10 as the smallest non-zero value. The largest value is 9 in the exponent position and 9 in the significant digits. Well, once again, this is going to have a very different interpretation and meaning than 999 in the previous system. A much different interpretation, because look at this. We're saying 10 to the 9th multiplied by 9.99. So we have 9.9 billion as the largest value that this proposal can encode, right? And so, wow, it seems like we've really pulled off something magical here. Sure, we can't represent 1/100th, but we can represent 9 billion. But do you see the catch? And the catch has to do with how many numbers can we represent in total using 3 digits. The total number of numbers has not changed, right? We have 3 digits available. There are only 1,000 different combinations of these 3 digits that we can come up with. So the catch here is there's only 1,000 numbers in this system that we can represent between 0.1 and 9 billion. And of course, there's way more than 1,000 numbers between those two values, right? So there's going to be a lot of numbers that we can't represent at all given this encoding scheme, and that might be a problem, right? So it feels like, though, on first glance that, wow, we've really increased the range of our number representation, and certainly we have. I also want to point out really quickly, because we're not going to have a proposal that goes in this direction, but if you imagine, well, what about 2 exponent digits and 1 significant digit? Well, this problem would be even more amplified, right? Where you would have orders of magnitude 10 to the 99th is a much larger number than I would even want to write out on a slide. But you would still only have between 0 and 10 to the 99th 1,000 possible numbers in that domain that you could actually represent and encode. So we have dramatically lower precision, right? If we think about on the low end of what we've got, we at the 0 exponent, we're still at we're not quite at 1/100th, we're at 1/10th between each position. But notice at the top end, for the largest numbers that we can represent in this system, there's 10 million numbers between the largest number we can represent and the second largest number we can represent, right? So if we think about the largest number we can represent, that's 10 to the 9th multiplied by 9.9, subtract 10 to the 9th multiplied by 9.8, right? And the difference of that is 10 million. There's 10 million numbers that we just can't even represent and encode in this system. So even though we can represent very large numbers, we've got huge gaps at the top range of our space. In fact, anything that's any number that is raised 10 to the 9th is going to have a gap of 10 million between it and the next closest number to it in this system, right? So there's a trade-off here. Yes, we can represent bigger numbers, but we lose some precision, right? And that fundamental trade-off is going to wind up being important to thinking about things in binary floating point representations as well. Notice there's an imbalance here as well, where on the low end, we actually do have quite a bit of, like 1/10 is a much smaller range of or difference between one number and the next than 10 million, right? So we've got some imbalance in the lower end of the numbers that we can represent. We actually do have a lot more precision than at the high end. And so there's a lot of imbalance here, and we might want to find a clever way of balancing some of this so that maybe we give up some of the precision on the low end, but we have more precision on the high end of our number system. So I want to introduce to you a modified proposal here. And this gets back to the second design question that I asked you to think about, which was, with only 3 digits, can you imagine a way of encoding negative exponents? So even though we can't actually have a negative number in that first exponent field, is there some way we could modify our formula to have negative exponents, which would allow us to specify fractional values or get more precision at numbers that are fractional or percentages? And the idea here is we're going to, again, make a trade-off. And what we're going to do is we're going to bias our exponent digit. And this is a funny idea that initially feels a little bit perplexing, but ultimately is pretty straightforward. The idea is whatever our exponent value is, we're going to subtract 4 from it, right? So if we have an exponent value of 0, that would be the same as 10 to the negative 4, because 0 minus 4 would be negative 4, and that's how we're going to get 10 to the negative 4. We have an exponent digit that's 9. 9 minus 4, we would think of that as 10 to the 5. So this bias is we're going to subtract 4 from whatever exponent is encoded in our system, right? So let's think about the smallest non-zero value we can represent. That's the 0, 0, 1. And using this bias, what we're saying is, okay, our new formula is 10 to the e minus 4, minus 4, multiplied by, and then our significand is going to be 0.1, right? So this is the same as saying 0 minus 4, or 10 to the negative 4, multiplied by 0.1. And of course, that's going to cause, if we think about 0.1, 1, 2, 3, 4, we're going to have a number that is ultimately 4 zeros followed by a 1 in our decimal position. So notice we've got much more precision. We can represent numbers much closer to 0 in this scheme because we have the ability to specify negative exponents with this bias, right? And so we can compute that out just like shown on the slide. Well, what about on our high end? Well, on our high end, our largest value that we can represent in this system is an exponent value of 9, but we're going to bias that. So this is going to be the same as saying 10 to the 5th. Right? So just to work this out again by hand, 10 to the 9 minus 4, which is going to be 10 to the 5th, multiplied by 9.9. Right? And so if we work that out, we are going to get a number that is less than the maximum number we could represent before, 990,000. But notice we're also now able to represent numbers much smaller than we were able to before. Which with a number much less than much closer to 0 than we could previously. So when we think about what is floating point and how do we imagine floating point in binary, it's going to be a very similar system. And I think that one of the best ways of visualizing the impacts and the ramifications of what floating point is by trying to give a table of values that looks like this, where notice if we think on this left-hand column, this is our exponent digit, but that's biased, right? So we still need to subtract 4 from each of these. And these are going to be our significand digits. And what we're saying here is, okay, the expression that we're going to use to evaluate what this means is 10 to the exponent digit, which is 0, minus our bias, which is 4, multiplied by 1.2 because our decimal is still implicit here, all right? And look at what's going on. We're saying, okay, this is the smallest, or by having an exponent of 0, which is biased to be negative 4, this allows us to represent numbers very close to 0, or much closer to 0 than we could otherwise. And each time we increase our exponent, so what this table is showing us is what happens, what is the ramification or the result of increasing our exponent digit one at a time. And notice what's going on is our exponent is increasing by 1 each time. So our order of magnitude is increasing by 1, which has the effect of shifting where our decimal digit is, right? So as we increase our exponent digit, our decimal position in our number is moving further away from 0, such that we have larger and larger numbers. We still only have 2 digits of significance in the number that we're representing in this system, but we've got quite a range of numbers. And so if you wanted to know where the name floating point comes from, well, it's this idea that here we have these fixed set of digits, but one of them specifies where this floating point is actually going to be placed. And as we change the magnitude of that, it has a ramification on what is the number that we're actually representing and encoding here, right? So the significand position gives you a sense of how much precision we have, right? So when we start talking about the high range, notice that the next biggest number we could represent here would be, this is our thousands place. So 130,000 would be the next largest number we could represent, because we could only increase this 2 to be 3. And that would give us 130,000. So there's a 10,000 number difference between, or level of precision between one number and the next when we're working at the high end of our exponent position. Whereas with on the low end, here we've got quite a bit of precision, right? The next lowest number would be 0.00011, and that would have a difference of tenths, hundreds, thousands, 10,000s, hundreds, thousands, 1/100,000th of a position is the next closest number we could represent. So we've made a trade-off here. By biasing our exponent, we get much more precision on the low end. We trade off, we can't represent quite as large of numbers, but when you think about like the fact that we can't represent even numbers within 10,000, a range of 10,000 or 1,000 or 100, as we move up into the higher levels of the exponents that we're representing here, that seems to be like an okay trade-off. And this certainly comes with a lot of limitations, right? We still only have 10,000 numbers we can represent with 3 decimal digits, no matter what system we're using. And here we've got still quite a range between this number and this number. You can imagine that having only 10,000 values between them seems like not enough. So the real limitation here is the number of decimal digits we're making use of. If we had more decimal digits available, of course, we would be able to represent many more numbers within these ranges of our domain. The key idea behind floating point, as we're looking at it in decimal notation, is that we're going to have an exponent, and that exponent here is based on the power of 10. When we look at binary floating point, it will be on the power of 2. We're going to have a bias, and what that bias gives us is the ability to represent numbers closer to 0 than we could otherwise, right? It gives us a lot more precision for smaller numbers, and the trade-off is we don't get to represent quite as large of numbers, but that is typically okay. The number of digits we give to our significand is ultimately going to give us the number of significant digits we can have in our resulting number. And so there's going to be this trade-off between how much space in our floating point number do we allocate for the exponent, and how much space do we allocate for our significand, and how do we think about the bias with relationship to those two things. Before we get into binary, let's talk a little bit more about this extended design proposal and just be sure that we understand the trade-offs here. So when we have one biased exponent, the smallest negative value, in this example, we are adding the ability to represent negative numbers. And so here I'm adding on a sign. And we're going to see that with binary encoding, there's going to be a position allocated for the sign as well. We'll just choose a 1 or a 0 for the negative and the other for the positive. Here we're going to say we're going to give space for a negative symbol or a positive symbol if we want it, right? And that gives us, by using one more position, we can add the ability to represent negative numbers. So we can represent negative numbers that are very close to 0 or very far away from 0, depending on the exponent that we're using, and we're still using a bias here. So notice we've extended this by only one position, which adds the sign, and now we can represent negative numbers as well as positive numbers, and we can once again see that we get more precision as we are closer to 0 and less precision as we get further away from 0, either way. In the next lesson, we're going to talk about floating point representations and finally get to the bottom of binary representations in floating point.